Hello, welcome back to another lecture. In this lecture, we're going to go ahead and find the shear moment diagram for this indeterminate beam using slope deflection method. If you take a look at the beam itself, we can say we got 3 reaction here, 4 and 3 is 7 reaction. We only have 3 equations, so this beam is statically indeterminate by 4th degree. And kinematically is about have a 1 degree freedom. What I mean by that, it's the slope and deflection here is 0. Slope and deflection on this end is 0. The deflection in the middle is 0, so but we only have a slope, so only have 1 degree of freedom. And as you can see on the board. So how we're going to solve this, we're going to use a method, slope deflection method, which is going to basically. So the step that requires for us to solve the indeterminate beam, continuous beam like this one, is the first thing you really want to do, find out the degree of freedom. What I mean by degree of freedom, you want to know at the joints where the supports are, what is the how many displacements you have. In this case, when you look at the fixed end, you know your deflection is 0, and you know your slope is 0. And on the other fixed end, same thing. Deflection 0, slope is 0. But in the middle where you have the pin, you know your deflection is 0, but your slope is not 0. So this is kinematically has a degree freedom, first degree freedom. So now once we calculated that, the next step really you want to do is divide the continuous beam into a member and joint like as shown. We would like to know once you divide that and you replace the end with the internal bending moment. And in this case, we have 2 members, which they are connected at the joint B. And we really don't care at this time for the outside joint for now, but we want to care about the middle because that's where you're going to use the equation of equilibrium to relate the bending moment with the slope deflection equation. Once we have broken everything down in this term, then the next step is we're going to go ahead and use the slope deflection equation. So basically, the slope deflection equation relate the unknown internal moment at the joints to the displacement of the joints for any span of the structure that we're working on. Now, the slope deflection equation basically is, if you look at it here, we have 2 different conditions. If we have the end span, as shown on the screen, the end span is pinned, then our slope deflection equation is given like MN is equal to 3EK theta nearest angle, rotation angle minus phi plus the fixed end moment. We're going to talk about fixed end moment in a second. And that's one equation we're going to use. And this but however, like in our case, because our both end is fixed, we're going to use this other equation, which is Mn is 2ek times 2 theta near plus theta far and minus 3 times phi and plus the fixed end moment. We're going to use these equation, and then once we have these equation, and then we have an equilibrium equation, all we have to do is use the equilibrium equation and substitutes for, and then we can find out the internal moment, and once we have internal moment, we can find the reaction, or we can solve the problem. So what is the fixed end moment? The fixed end moment is the fixed end moment can basically be calculated based on a given shape from end of your book, or you can Google it someplace else, and that's what we'll be using. All right, let's go back to the video. What we're going to do is calculate the fixed end moment first. Fixed end moment at BC, which will be BC right here. Since there's nothing on the other side anyway, so we're going to focus on member BC. And that's going to become, shows on the board, it's going to be minus WL squared divided by 30, which is equal, we have 6 times 6 squared and divided by 30,
and that gives us negative 7.2 kilonewton meter. And then we're going to go ahead and do the fixed moment of CB, which is equal W squared over 20, and that's going to be 6 times 6 squared divided by 20, and that comes out to 10.8 kilonewton. All right, now we have that. Again, we're going to go ahead with the equation 10.8. We're going to use that equation, and we're going to calculate different moments. So MAB, let's start out with moment MAB right here. And based on the equation, MAB is equal 2 times E times I divided by 8. And that's going to be multiplied by 2 times theta n. Theta n means the slope near. So theta n for this is what? It'd be 2 times theta n. So theta n is theta a. 2 times theta a, and theta a will be 0. So it'll be 2 times 0, because we know theta A is equal to 0. Theta B we don't know. And theta C is equal to 0 also. So then, but we're working on this number AB. It's going to be 2 times theta n plus theta far away, which is theta B. So it's going to be plus theta B and minus 3 times phi. And phi is, let's see if I have a room here. Phi basically is delta divided by L. So we know at A, the slope delta is equal to 0, so it becomes 3 times 0. All right, and then the next thing we have is plus FMEN. The fixed end moment between this beam is 0 because there's no load there. So plus 0, and that comes out to EI divided by 4 times theta B. So that was MAB. Let's do MBA. And that's going from this end. So we're going to have 2EI divided by 8 multiplied by 2 times. Now theta near is going to be theta B. So 2 times theta B plus theta far away, which is going to be that corner. It means it's theta A, which is 0, minus 3 times 0 because deflection is 0 over here, and plus 0 because there's no fixed end moment on this end. So that comes out to EI theta, EI divided by 2 theta B. All right, now we're going to go focus on that was for member AB. So this is basically member AB. And now we're going to go ahead and go to member BC. So we're going to have MBC, which is equal to 2E I divided by 8. No, it's going to be I divided by 6. That's right. The length is 6. And multiplied by, we're going from here, so theta near is going to be theta B, 2 times theta B. Yep. And then theta far away, which is a theta C, that's equal to 0, plus 0 minus 3 times 0 because deflection is 0 on this corner, and plus the fixed end moment of BC. BC came out to minus 0.72 kilonewtons. So that's a minus here, minus 7.2, which is equal 2 EI divided by 3. I'm not going to have a rough one. So MBC comes out to 2 EI divided by 3 theta B minus 7.2. Let's continue this right here. And now next one we're going to have a MCB, which is equal 2 EI divided by 6 times 2 times theta near is equal 0. So that's a theta C, and plus theta B minus 3 times 0. Deflection is 0 again. And that's plus 10.8, because the fixed end moment CB is 10.8. 10.8, which is equal, so MCB comes out to EI divided by 3 theta B plus 10.8. So now I have 4 equations. I got 1, 2, 3, 4 with 5 unknown. 1 unknown, 2 unknown, 3 unknown, 4 unknown, and theta B, 5 unknown. So we need the extra equation to solve this, and a 5th equation. Where'd that come from? It comes from the slope. And it comes from the, it comes from the joint's equilibrium. And we know the summation of moment is equal 0 at any of these joints, but we need to focus on this one in the middle, so we know summation moment at B is equal 0. So when you go 1, 2, 3, 4, I have all those, and the next equation that I need is the summation moment at B is equal 0. We're going to explore that. I need to erase this board before actually I can come over here. Let's bring this over here for summation moment at B is equal 0. And summation moment, what do I have? I have MBC and I have MBA. That's the only 2 I have. Therefore, I'm going to say MBA, summation moment at B is equal 0. I got MBA plus MBC is equal 0, and MBA comes out to EI divided by 2 times theta B, EI divided by 2 theta B, and then MBC is 2 EI divided by 3 plus 2 EI divided by 3 theta B minus 7.2 equals 0. And from here we know theta B comes out to 6.17 divided by EI. Okay. Let's write that a little bit better. Okay. So now we have theta B. And we're going to go ahead, I'm going to go ahead, take theta B, substitute in all those equations. So if we substitute in all those equations, we're going to end up with, we're going to find out that MAB, let's write this with a different color, MAB equal 1.54 kilonewton meter, and MBA comes out to 3.09 kilonewton meter. And then we have MBC comes out to minus 3.09. And MCB, we have room here. MCB comes out to be 12.86. So that's all my moment. That we just began here. I need more room here before we continue. Now we have this. Pause the picture and write all this stuff down because I'm going to erase the board. 1, 2, 3. Calculated all the moment. Let's put them in the free body diagram here. So this one came out to be 1.54. 1.54. And then over here came out to 309, this moment, in internal bending moment. This became 3.09. And let that be, and then this is BY left, and this is BY right. So BY, we're going to calculate, MBC came out to be 3.09. 3.09, and MCB came out to 1286. Okay, now we have that. Let's calculate the reactions, force, and once we have that, we can go ahead and do the shear moment diagram. So what would I do here? I have the moment here, I have the moment here. How do I calculate the reaction? Well, let's take a moment about point A, right? Summation moment about point A is equal to 0. Counterclockwise is positive. So I'm going to have BY, left BY, time, this is 8 meter. And that's going to be positive. And then I'm going to have minus 1.54 minus 309 equal 0. And that will give me BYL comes out to 0.579. 0.579. So that's BYL. And then I do summation F of Y is equal to 0. And AY comes out to negative 0.579, which is going downward. So that's going to become 0.579. Okay, so now we have this, and we have this. Now we're going to move over to this side here and find BY right. And move into this member, try to figure out the reaction in this member. And simply, we're just going to do the same thing over here. Take a moment about some point C. Summation moment about point C is equal to 0. And we're going to have minus BY of right times 6. Then it's going to be plus, the constant of force is going to come out to 18 because it's 1/2 of 6 times 6 is 18. I mean 1/2 of, yeah. So 1/2 of 6 is 18. And plus 18 times 2, that distance is a 2 right here. 2 meter. And then we have both moment, which one of them is plus 309 minus 1286. And BY right going to come out to 437. So that comes out to 4.37. You do summation of Y, and then this one come out to 13.63, which I already wrote it down. So now we have all that done. We're going to go ahead and go up in the beam right here. Okay, I don't want the video to get too long, so I erased the board and I rewrote some stuff. We already have this information. So after we come back in here, let's take this here and put all the information that we have calculated. We know the moment, we know the reaction of each one of them, and we want to do the shear moment diagram. So we bring this down and we draw the shear diagram, pretty easy. But we'd like to know how we got 1096. Because right here where shear is equal to 0, you have a maximum moment. How do I have that? If you know that, good luck to you. If you don't, this is how we do it. So we're going to come back and look at the member CB, and we're going to go ahead and take member CB and then cut it someplace that we like to say, okay, where share is going to become 0. We don't know that distance, so we call it x. However, we have this, we know the slope of this line is 6 over 6 is equal 1, so that become x. The magnitude right here become x. And therefore, my resultant force is going to become 1/2 of x times x, which become x squared divided by 2. And my share is going to be 0 at this point, at point x. And I already have my reaction is before 37 I have calculated. And we know moment at this point is internal moment is at 3.09. So what do? I take summation f of y is equal 0. I have 437 minus x squared divided by 2 plus 0 equals 0. And therefore, x comes out to 296. And then I know this distance where share is equal to 0 become 10.96. And then go ahead and put that number, take a summation moment about this corner at x is equal to 296. You can calculate your moment comes out to 553.